The eclipse on August 21st provides us with a unique opportunity. It's going to be the first transcontinental eclipse in a long, long time. So what we're going to do is image the sun's atmosphere, this hot outer atmosphere, using the VLA at radio wavelengths at more than one frequency, because at different frequencies we probe to different depths in the atmosphere and different temperatures. I've been interested in the sun's corona for many years for the following reason. It's been one of the outstanding problems in not just solar physics, but also the physics of other stars, because other stars behave in similar ways to the sun. And the problem is this: the sun is a sort of normal middle-aged star. It has a surface temperature which sounds pretty hot. It's about 6,000 degrees Kelvin. That's about 10,000 degrees Fahrenheit. Something kind of magical happens in the outer atmosphere of the sun. The corona that I mentioned, that you actually can see with your own eyes during an eclipse, is about 2 million degrees, much, much, much hotter. So it's heated somehow because the star is relatively cool and interstellar space is relatively cool. So what heats this gas to 2 million degrees? You might expect that the temperature would continue to decline as we sort of continued above the visible surface of the sun, but something very interesting and very mysterious happens at that point, and that is that the temperature reverses. In other words, it begins to increase with height. With radio waves, we can actually see those layers of the sun where the temperature is beginning to increase again. This takes us through a layer called the chromosphere, which is just above the photosphere, the visible surface of the sun, out into the corona. Now, the corona we usually can't see with our naked eyes, but during eclipses, which completely blocks out the photosphere, the moon blocks out the photosphere, we can in fact see the corona extending well above the visible surface of the sun, and it's a very beautiful thing. What radio waves allow us to do is anytime we can use instruments like the Very Large Array to observe these layers of the sun from the chromosphere all the way out into the corona and try to understand in more detail the so-called coronal heating problem. So solar activity and coronal heating are both of keen interest, and magnetic fields are thought to play a central role. Now, there are two broad theories that are thought to play a role in coronal heating. One is that multitudes of tiny flares, nanoflares, which draw their energy from the sun's magnetic field, take place at all times and heat the gas. Another possibility is that waves, which originate in the low solar atmosphere, propagate up, guided by the magnetic field, and dissipate their energy in the atmosphere, thereby heating it. The interesting about the sun and radio astronomy is that we're actually at about the 70th year anniversary of radio astronomy as a real science discipline. It was in the 1940s and the post-war years that radio astronomy emerged as a real scientific discipline, and the sun played a central role in that. It was the first bright object that could be studied in some detail, and a lot of the techniques we now use, including those at the VLA, were first developed during those early years.